Hello and welcome. Today, we take a question from the Putnam competition exam that is considered one of the easier problems, but it contains a hidden trick. We are given the equation 2a power n plus 3b power n is equal to 4c power n, and we want to determine all positive integers n for which there exist positive integers a, b, c satisfying this equation. So, let's start by experimenting with some values. We start from the smallest value, that is, n equal 1. By putting the value of n, we end up with the linear equation, that is, 2a plus 3b equal 4c. With a little trial and error, we can find solutions. For instance, the triple ABC equal 1, 2, 3 works. Putting these values, and it becomes 2 into 1 plus 3 into 2 equal 4 into 2. By simplification, it becomes 2 plus 6 equal 8. By adding this, we get 8 equal 8. So, n equal 1 definitely works. Now, the question is, are there any other values of n? At first glance, this problem resembles the famous equation x power n plus y power n equals z power n, which, by Fermat's last theorem, has no positive integer solutions when n is greater or equal 3. That suggests a possible conjecture. Maybe our equation also has no solutions for n greater than or equal to 3. Let's try to prove this. Suppose we do have a solution for some n greater or equal to 3. Let d equal GCD of ABC. GCD means the greatest common divisor, and we define new number as x, y, and z, divided it by a common number d. So x equal a by d, y equal b by d, and z equals c by d. Let's see what happens when we substitute x, y, and z into the original equation. So let's begin by substituting x and y into the equation. So we have 2x to the n plus 3y to the n. Is that equal to the 4z to the n? By the definition of x and y, we can substitute in, and it becomes 2 into a by d whole power n plus 3 into b by d whole power n. Now take a common factor of 1 over d power n, and it becomes 1 over d power n into 2x to the n plus 3y to the n. But we know that since a, b, and c is a solution, this sum is equal to 1 over d power n into 4 into c to the power of n. This is equal to 4 into c divided by d power n. Here c over d equals 4 into z to the power of n. So in fact, 2x to the n plus 3y to the n equals 4 into z to the power of n. If we have a common solution a, b, c, where d is our greatest common divisor, we can then derive another solution by dividing each of these by the greatest common divisor, which means, without loss of generality, we can suppose that a, b, and c are relatively prime. Their greatest common divisor is equal to 1. So with these assumptions, we will now work to show they share a common factor. So starting with the original, subtract 2a to the power of n from both sides. Now on the right-hand side, take 2 common. Now it becomes 2 into 2c to the power of n minus a to the power of n. Since the right-hand side is equal to 2 multiply some positive integer, we have that. 2 divides the left-hand side, which is 3, into b power n. But we know that 2 does not divide 3, so 2 must divide b power n. Since 2 is a prime number, this means that 2 divides b. In other words, b is an even number, and it is equal to 2k for some positive integer k. Substitute this into the original equation, and we will use the same strategy to show that a and c both have factors of 2. So, subtract the k term from both sides of the equation, and then divide both sides of the equation by 2. Notice that the right-hand side will have a factor of 2 in each term. Thus, 2 must divide a to the power of n, which means 2 divides a. Therefore, a is in fact an even number equal to 2m. So, we have shown that both b and a are even numbers. This, in turn, implies that c is also an even number. Substituting these into the original equation, we then divide both sides of the equation by 4. What remains are terms that both have a factor of 2, and notice it is very important that we assumed n is greater or equal to 3. Why we assume this? Because in our argument, we used the factor 2 to the power of n minus 2. When n greater or equal to 3, this guarantees that 2 divides c power n, which means c is even. But now we have shown that 2 divides a, b, and c. This means all three numbers share a common factor of 2, which contradicts our assumption that greatest common divisor of a, b, c equal 1. Therefore, there is no solution when n is greater or equal to 3. Now, here's the story gets interesting. It would be nice if the same proof worked for n equal 2, but there is a little twist in the plot. If n is equal to 2, then the factor 2 power n minus 2 is equal to 1, and suddenly our clever trick no longer works, and we can no longer conclude that 2 divides the critical term. So, the case n equal 2 must be treated separately, almost like a bonus challenge level in a game. And that's the beauty of math. Sometimes the argument works smoothly, but every now and then a special case keeps things exciting. We suppose there is a solution with n equal 2. Without loss of generality, let's assume GCD of ABC equal 1. Again, we try to show that all three numbers must share a common factor, which would lead to a contradiction. Let's look at the original equation modulo 3, 2a squared plus 3b squared equal 4c squared modulo 3. A squared is congruent to c squared modulo 3. By rearranging it, a squared plus c squared is congruent to 0 modulo 3. Now, the quadratic residues modulo 3 are only 0 and 1, so 0 squared is congruent to 0. Modulo 3 1 squared is congruent to 1 modulo 3. 2 squared is congruent to 1 modulo 3. So the possibilities for a squared and c squared modulo 3 are 0, 0, 1, 0, 0, 1, 1, 1. The only way their sum is congruent to 0 modulo 3 is when both are 0. Thus, a squared is congruent to 0 modulo 3 and c squared is congruent to 0 modulo 3. It means that 3 divides a and 3 divides c. Now substitute back into the original equation. Rearranging gives a multiple of 3 on the left, so dividing through shows that 3 divide b squared, hence 3 divide b. So we have shown that a, b, and c are all divisible by 1. This contradicts the assumption that their greatest common divisor is 1. Therefore, there is no solution when n equal 2. The only positive integer n for which there exist positive integers a, b, c satisfying 2a power n plus 3b power n equal 4c power n is n equal 1. I hope you enjoyed the video. If you found something interesting, don't forget to like the video and subscribe to our channel for more.